All right, we are about in time, so I'll be starting. Thank you very much for joining. I am Arno. I am the development lead at ThinkCell. We are a software company in Germany, and I still do quite a bit of hands-on development, and I'll be talking today about the C++ rvalue lifetime disaster. That sounds pretty dramatic. At the end of the talk, you'll decide whether it's really that dramatic, whether it's a small disaster or a big disaster, but it will be about rvalues. So why do we have rvalues? The standard library advocates value semantics, as you all know, and up to C++ 2003, that is a long time ago, that lead to frequent copying. Because whenever you have one of these values and you put them from one container into another container, for example, you need to copy them. And rvalue references were originally designed to fix this. So instead of copying, we would do more efficient moving, which means that you can steal the resources that one object has to build another object. And you leave this other object, the source object, you leave empty. And that way you avoid unnecessary memory allocations. Now, here's an example. Say you have a vector of vectors, and you're moving, or you're putting another vector into that vector of vectors. And by the means of that moving, we avoid the copy. The memory that the vector we're going to move in allocated is being reused for the vector that's inside the vector of vectors. Now, rvalues were used for another purpose, and increasingly so. The C++11 already started using it in the cref to manage lifetime. What they actually did is that cref is a wrapper for reference, and that was meant to be a reference, an lvalue reference, not an rvalue reference. So when you would try to create such a cref from an rvalue, it wouldn't build, it wouldn't compile. And now with C++ 20, ranges were introduced, and ranges contain references to containers in particular. And these ranges may dangle if that container goes out of scope. So if you have something like this, you are building a std vector, and then you are applying a filter, the resulting object will not actually do the eager filtering. It will be a lazy view on that vector, and that lazy view that will only filter actually when you iterate over it will have a reference to the vector that it's actually filtering. And if that vector is an rvalue, like here a temporary, there is a danger that that temporary will go out of scope, like it would do after this line would actually finish. And then you would have a dangling reference. And to help you avoid that, these views wouldn't compile if you put in an rvalue reference instead of an lvalue reference. Before we go into these lifetime problems, let's talk a little bit about the pitfalls that rvalues have and how we can avoid them. So here are the few basics of rvalues and how to use them. So let's say you have a function foo, and that function declares a variable and returns that variable. So you want to do that as efficiently as possible, right? So let's say that variable is const, and in order to be efficient, we will try to move it when we return. Now, as many of you probably know, this doesn't work because you cannot move out of a const object. So let's try to remove the const and see if things get better. And indeed, they will get better. You will avoid the copy and you will get a move, but we can actually do better than that. C++ lets us do something even more efficient, which is to elide the copy altogether. So if you have something like this, you just don't put the move around the A. If you just return the A as it is, what happens is named return value optimization. So the compiler will put the A that you declared inside foo actually already in the place of the return object. So into the place where the caller wants it. You don't have to move it or copy it anymore. It's already in the right place. And that's, of course, the most efficient that you can be. So we learn here, std move can make things worse. Now, what happens if you now put the const back in? Well, turns out that works as well. The NRVO still holds, it still works, even if you have a const object. So you may say, well, so const can't be that bad. Well, let's say you have a condition and you are creating two different kinds of A's. And the first A is returned under some circumstances, or the second A. Now, in that case, well, NRVO, named return value optimization, doesn't work anymore. The reason being that the compiler can't decide at compile time, unless it's really doing deep analysis of the code, it can't decide in general which A to put into that return value spot. It doesn't know which A you potentially want to return at the very end. So it actually does a copy in that case. It will just create the A on the local stack, and then it will copy. And again, you will get a copy. You don't get a move here because the A is const. You can't move out of a const object. So again, you want to remove the const. So what do we learn from all that? Oh, there's another one. So let's say you have a structure, and that structure contains a member. And you want to return the member, and that structure is local, and you return the member of that structure. Now, you would think, well, it kind of looks like you have a local variable, right? And you return, and so you should get, well, maybe you don't get NRVO because the return value spot only has room for an A. It doesn't have room for a B. But at least you should get a move. Well, you don't. The members don't automatically become rvalues, so just because you write return in front of them. What you can do, you can write the move around the structure. And then the structure is an rvalue, and a member access to an rvalue is actually an rvalue itself. So in that case, you would actually get the move. You don't have to write the move around the b.ma. And if you think about it, it kind of makes sense to write it this way, because you are marking the b as the thing that you don't need anymore. That's the thing that's going out of scope. That it contains a member, well, that's kind of, yeah, it contains a member. It could contain something else, but you really want to say the b is what I don't need anymore because it's going out of scope. Now, what do we learn from that? Recommendations are, don't make return values const. It may work if you get named return value optimization, but as you've seen in the case of the if you then later on introduce the if, it's very easy to forget to remove the const. So my recommendation would be return values, don't make them const. And there's also a Clang warning, WM move, which lets you point out all the places where the move may be pessimizing. So that's a good thing to use if you want to find out whether you or someone else in your code used something pessimizing regarding move. All right, so let's go into a little more detail. So we want to talk about the temporary lifetime extension. What is that? Let's say here you have, again, a structure A and a structure B that contains the A. And we've written an accessor for our A, as we do very often. And now this returns a constant reference to that A, and we store that inside a constant reference. Okay, that's pretty simple, right? So nothing special here. Now, let another structure enter the picture. It also has a get A, but in that case, that get A is returned by value. Now, let's say you have generic code that either takes a B, which returns by reference, or the C that returns by value. And you just write get A to generically say, well, I need the A, right? I need to store it somewhere. So you write autoconst reference. Now, this actually works. And the reason that it works is a quirk in C++ called temporary lifetime extension. What it basically says is if the reference that the get A returns gets captured in a local variable, I'm going to extend that reference to that temporary to the end of the function, so that reference stays valid until the end of the function. And the idea was, back then, that was actually before auto, to just say, okay, you can basically write constref, and the right thing will happen. It will automatically do the right thing. And that all predated the rvalue references. Now, let's see how that goes. So let's say we have, again, two structures C, right? Two instances of that structure. And they both, you want to calculate, you call get A, and you want to calculate the minimum of these two A's and store that, right? Does that work? And remember, the get A returns by value. Now, as you probably suspect, that doesn't work. The min takes its parameters by const reference, and it returns them by const reference. So the get A value, the value returned by get A, gets bound to this const reference left-hand side and right-hand side, LHS, RHS, and one of them gets returned. And then the auto constref obviously doesn't know anymore that this is something special, that this is a value that's being returned, and it doesn't do any lifetime extension. So then you get a dangling A, which is bad. Let's try to improve on that. So first of all, it was pretty obvious that if the std min throws away the rvalue-ness of the arguments, then well, if you throw it away explicitly, then you won't recover it, right? So we shouldn't do that. So we should really be careful, and we should pass through the rvalue-ness of the parameters of the arguments of min to the return value. So make that an R value as well, and that's what I've done here. Okay, so we wrote our own little min function that passes through this rvalue-ness. That's the first thing we have to do. So does it work then? Turns out, no, it still doesn't work, and the A still dangles. The problem here is that this temporary lifetime extension only works if you actually have a temporary. So that's a value. If you have a reference, an R-value reference in particular, even if you have an R-value reference, it doesn't do anything because it doesn't have a value. And it would only be able to do this by actually creating a copy, right? So the R-value would have to be copied. And the temporary lifetime extension doesn't do that. So what do we do? Let's see, here's another problem of temporary lifetime extension. Let's say we have two functions. Either there's some A that returns by value or some A that returns by reference. And we want to write a function foo that is a kind of a forwarding return. It takes the value from some A or the reference from some A and returns it unchanged. That's easy to write, as you can see here, if we simply straight away return some A, right? Well, good enough. And we write decal type auto, so whatever reference you're getting from some A or value you're getting from some A is whatever foo is returning. You'll get the same return value from foo as the sum A has in this particular circumstance. Now, let's say we want to do some code, put some code in between, right? So we want to take the A from the sum A, then do something, maybe look into it, and then return it. So how would that work? Well, let's try again with temporary lifetime extension. So you have an auto constref A, sum A. So far, so good. There, lifetime extension will work. If sum A returns a value, then A will keep that value alive. Then you do something, and then you return it. Well, the problem is the decal type auto will assume whatever the declaration type of A is. And that declaration type is still auto constref. It's not a value. So foo will return a reference even if sum A returns a value. That's not good. So we could try to improve by, instead of decal type auto, we use auto. Well, then we get a value. But we get a value all the time. Even if sum A returns a reference, we still get a value, which is also not what we want. Now, the problem here is, the underlying problem of this temporary lifetime extension, which is why I don't like it, is that it's really lying about its type. It always tells you it's a reference, even if factually, it's really acts like a value. It's really indistinguishable of how it's behaving inside the function and how it came about. I mean, it got assigned from a value. You can use it like a value inside your function. But then if you ask it for the type and you're doing something with some reasoning about the type, it tells you, oh, I'm still a reference. And that's not so great, in particular because we are using more and more generic programming where types are important. The same code may act on different types. So we should really know about, should be able to find out what the real type is. My advice, throw this temporary lifetime extension away. So that's no longer good in the world of rvalues and of generic programming. This temporary lifetime extension has reached its end of its useful life, I think. Now, what we really want is we want to automatically declare a variable, either with auto, if we construct it from a value, or from an rvalue reference, because the rvalue reference will die soon, so we have to rescue its value into somewhere. Or you want to use an lvalue auto constref if we construct it from an lvalue reference. Now we can write such a contraption, right? So here there's a macros to the rescue, that whenever you are giving it a value or an R value, it will actually decay. It will use the decay to turn it into a value. And you give it an L value reference, it will just keep the L value reference. And now if we, instead of this lifetime extension, we use auto cref, this macro that we introduced, then things will start to work. So if we do this, for example, auto cref a sum a. Now, if the sum a returns a value, a will be a value. If the sum a returns a reference, a will be a reference. So everything is good. Now, be careful. Don't add any parentheses here, because the decal type auto will adopt whatever the decal type of the a is. And if you write it without parentheses, you will get the declaration type. So that's the type that this variable a is really declared with, which is, in this case, it's a value or an L value reference, depending on what sum a returns. Now, if you put parentheses around it, that expression type is always going to be a reference, which is then you again have a dangling reference when you return the a with parentheses around it. We actually use this auto cref a lot. We make it pretty much our default auto, and it does the right thing in surprisingly many places. So and it up to C++17, it didn't work inside with lambdas. So when something on the right hand side of that auto cref contained a lambda, it didn't work. But that's been now fixed in C++20. So you can use it in even more places. So auto cref turned out to be very practical. Now, there's one choice you can make. The auto cref that I had on the previous slide was non-const when it contained a value. That's good for returning, but of course, maybe you want to protect yourself against inadvertent changes to that variable, because conceptually this thing is really const, because I mean you put it there because you may take this thing by auto constref. In that case, it is really const. So conceptually, it's probably const. And we actually made our auto cref by default const. And if you want to return that value, you have a different macro that declares the value non-const. And if we now use that for our little problem that we have, this minimum calculation, we still have our own minimum implementation that forwards the R value. And then for assigning that minimum to the A, we use auto cref. And so the R minimum then returns the correct R value reference. It basically tells auto cref, hey, I'm going to go away. I have something here that goes away very soon. And then auto cref says, OK, if you have something that goes away very soon, I'm going to store it in a value. And then everything works. OK, let's look at another example here. And we are starting really to get to the deficiencies of C++. We have a structure A, and a structure B that contains the A. Now, if we assign this to A, we just say B, and this is an R value, B.ma assigned to A, then A will make a copy of the BA because it knows that it's an R value, right? Because as we've seen previously, members of rvalues are rvalues. Now, that all works. So let's say we replace that member with an accessor, which we do all the time, right? So we write an accessor get A that returns a const ref. Now we do the same thing. We just write B, rvalue, and then get A, which is calling our accessor this time and not the member directly. We made the member private, as you should. But now what happens? It doesn't work, because the declaration type, the decl type of B get A is of course now a const ref. That's how get A is declared. Now, if the A is const ref, the auto cref doesn't do a copy, and then the whole thing dangles. What can we do? Now let's try, maybe if you put an ampersand there, right? We really want an L value reference, and ampersands, they are for L value references. Except that doesn't make a difference at all. This is purely syntactic sugar, and semantically, that's exactly identical to just writing const. It's not good. So the fundamental problem is that this const ref binds to anything, including rvalues. So we have this thing in the language, const ref, that silently turns rvalues into L values. And that actually affects any accessor that we write. And there are many of them. Code is full of them. So let's see how various parts of the language deal with this problem. Let's look at the ternary operator. Let's say we have two functions, L and R. And L, as the name suggests, returns an L value reference, and R returns an R value reference. Now, what's then the decl type of a ternary operator that has two L's? Well, not surprising, it's a const ref. So it kind of preserves the value, the type of the L. Now, what's the decl type of purely R values? Well, it's the R value reference. So no surprise there. Now let's say we combine these two. We have an L and an R, and we combine these two and calculate its type. Now, of course, here it's be like, well, the const ref does take these R value references, right? So maybe we should be an L value reference. But then we would kind of forget about this R valueness. So what did the language do? It's a const. The type of this kind of expression of the ternary operator between an R value reference and an L value reference is a value, a constant value at that. And if you think about that, well, this kind of forces C++ to do a copy. So if you're writing a line of code where you say decl type auto of A equals the ternary operator, and you have the ternary operator takes an R value and an L value, it will actually create a copy, and your variable that you declared will actually be a value. Okay. So there's another thing where basically, or another means to combine references. C++20 has a new trait that's common reference T, and that was actually invented for C++20 ranges. With ranges, you have the problem that say you have a view which merges two ranges. You have two ranges there, or say two containers. These two containers are sorted, and you want to lazily combine them into a single range that you can iterate over. A single, then as well sorted range. So like one step of a merge sort, essentially. And if you want to do that, then the iterator of that merged range has to accommodate both the returns of the two iterators of the source ranges. And for that, the library uses the common reference trait. And now you can ask, well, how does it behave? Well, for two L value references, no surprise. For two R value references, again, no surprise, it's an R value reference. But you can mix the two. Now, drum roll. It actually decides R value amnesia is fine. I'm just going to say it's a const L value reference. Okay. Here's another thing we can try. What if we use a value and a lvalue reference. I mean, semantically, this is not terribly different, right? Because as we've seen from the our min that we implemented, it's quite easy to turn a value into an rvalue. You just pump it through some sort of forwarding function, like the minimum function, where it either forwards one the left hand side or it forwards the right hand side. But in the process, any values that's there is going to be returned as an rvalue reference. But in this case, actually, the common reference will say it's an A. So it will turn it into a value in that case. So as a summary, we can say the common reference embraces rvalue amnesia. So it says, oh, that's a fantastic thing. Which begs the question, what's correct? Where is really the problem? And we want to look into that now. When we are talking about rvalue references and lvalue references and const references and non-const references, we are really talking about properties of these references. So for rvalue references, we assume that the lifetime is short. These things die pretty quickly. It's a temporary. Now, lvalue references, on the other hand, have a long lifetime. And const references are immutable, and non-const references are mutable, of course. There's one more aspect to references, which is kind of scavengeability. So if an rvalue, a mutable rvalue reference, you can steal its resources because you can assume that this thing will die pretty soon. You wouldn't want to do this, for example, from an lvalue reference because, well, then other people may still use that lvalue reference and then are missing their values. Nothing is stored anymore in your variable because you stole it. You scavenged it. This is what current C++ reference binding is doing. So rvalues, const lvalue reference, like binds to anything. Then rvalue, immutable rvalue reference binds to a constant rvalue reference, and the constant rvalue reference again, yeah, binds to constant lvalue reference. It binds to anything. Now, the problem here is that we are strengthening the lifetime promise, right? There are arrows that go from something that has short lifetime to something that has a long lifetime. So you overpromise, underdeliver. You have a short lifetime, but you promise you have a long one. And that cannot work. Now, what we have to do instead, we have to turn this around. We have to say, we have to go always to the weaker promise. So anything can really bind safely to a const rvalue reference because it has the least mutability, nothing can be changed, and it also has the least lifetime. So it's safe, anything can bind to it. Now, so less lifetime is okay, less mutability is okay, and there's one arrow missing here, which goes from lvalue references to an rvalue reference, because you would give this lvalue reference kind of scavengeability. You would allow others to steal from it, which was not what we want. So we have to leave this arrow out. We can't. This is again something that we cannot promise that you can safely steal from this reference. So now we have this, but C++ isn't like that, and that's very sad. And we dug ourselves a hole and we fell into it, and now we are sitting there and we don't really know what to do. And so what do we do? Is there a chance to fix C++? I should say up front, I didn't try this. I didn't hack Clang. I didn't try this on a large code base. It seems plausible to me. If you think otherwise, I'm happy to discuss. But these are my ideas, and you can hear me out and see what you think. First of all, what are the requirements? Certainly, existing code must continue to work. We can't just say, oh, we're going to throw away all the code and restart from scratch. It's never going to work. Now, even existing libraries have to continue to work. People rely on libraries all the time, and these existing libraries have to work even if we are using new code. So when we are using our new rules for binding, that, that has to cooperate nicely with existing libraries. So we need to be able to gradually introduce these new rules into a single code base. The idea is that any reference that we have that has basically this other little static property, that it either binds according to the new rules or the old rules. So either it's the const ref binds to everything, or the const lvalue reference binds to everything rules. The good thing is that reference binding only happens at the very beginning of the reference lifetime. After the reference came about, and once it's there, everything is unchanged, everything is good. So we don't need extra types. The type of the reference is fine after it's been corrected, after it's been constructed. I suggest pragma to the rescue. Let's say we have a pragma that enables or disables new binding rules. So you say, okay, you declare an auto const ref A. Now the old rules apply. You switch on your new rules. Now the new rules apply for the B, and you switch them off again, and then the old rules apply again. Now, in order to see what the consequences could be of doing such a thing, let's take a look at all the places where references are initialized in the language. And I try to make an exhaustive list, and let me know if you think of anything else. So first of all, we have variable initializations, either locally or globally. We have structured binding. Either, again, could be local, could be global. We have functional lambda parameter lists, which are binding references. Whenever they are called, they are references bound. Now, we have members of structures that are directly initialized as PODs. And we have member initialization in constructors. And then finally, we have lambda captures. That's all I could come up with. Now, you can imagine any one of these constructs now either being inside one of these pragmas or not, and behaving one way or the other, depending on where they appear. Now, this would kind of look like this. So you have a declare a void A, and that's outside of our pragma. There, the old rules apply. And if you call it with A5 down there, this compiles because your 5 is an R value, but in const reference takes anything. Now, if you switch on the new values, then the B5 would no longer be okay, because the const lvalue reference, according to the new rules, does not take R values. You would declare it as int const ref. So you can imagine your int const R value reference becomes the new lvalue reference. Whenever you have a function that just takes something and doesn't store it, just looks at it, and then it's done with it, you would no longer write const reference. You would write const R value reference, because you are happy taking R values. So in this case, the C5 would actually compile. Now, if you are calling then the C with an L value reference, like at the very bottom with an L value reference to an int A, this would also compile under the new rules, because the const R value reference can take L value references. Now, probably you would want that if the declaration and definition uses different binding rules, that this would something that the compiler would flag and not compile. So if B here would be declared with the new binding rules in effect, and then instantiated or defined with the old binding rules in effect, that wouldn't compile. It would say, well, you have to decide for one way or another. So what would be the impact on the standard library? We probably would need a feature test macro, because there are probably places where it's convenient to find out which mode you are currently in. Functions can be implemented equivalently. It's basically just replacing the const L value reference parameters with const R value reference parameters, because they would have exactly the same semantics. The only thing inside type traits that I could find where it would make a difference is the common reference. There you would have to have a new version and an old version, depending on the binding rules. Now, I couldn't find any other type traits that would be affected. Okay, obviously we haven't done this yet, and C++ is still the plain old C++ that we always had, and we have to somehow live with the situation. So what can we do? Well, first of all, I already said it, throw away temporary lifetime extension. It doesn't play well with rvalues in general, and you can replace it with an auto cref that we've already defined. Now, member accessors, I also said, are very problematic because you really should delete rvalue accessors. You should prevent this rvalues silently turning into lvalues. You may not want to define anything by default because, I mean, there's probably a reason that your member is private. And you probably don't want to scavenge it without, checking the internal implementation, whether that's okay or not. So we have a macro for that. And we simply delete the rvalue accessor, and and if someone really uses a class accessor with an rvalue, then we have to think about explicitly how we want to handle the situation. Now, the common reference can also be re-implemented, and the implementation maybe looks a little bit confusing here. What this really does is really not terribly difficult. So the old type is still, but you basically just calculate the common reference according to the old rules. And then you check if there was this magic rvalue to lvalue conversion. So you say, okay, if there's an lvalue reference of the old type, and you have any rvalues among your list of types, then you really want to supply an rvalue reference. You don't want to have an lvalue reference. So you take away the reference and add the rvalue reference. If that's not the case, you can just use the old type. Someone asked, how would this idea work with forwarding references? It doesn't work. It doesn't work any terribly differently. You would simply write in a forwarding reference, and it would take the type that's, the forwarding reference is the most flexible. So whatever you give it, that's the type what it would be. That's how it would be, how the template would resolve. So so there it wouldn't really make any difference. So yes, so member functions, you say, Peter asks whether I said that member functions are actually callable on rvalues. Yes, I said that, that they are callable on rvalues. So here's another mitigation we can do. We had this problem of ternary operators. And this ternary operator turning rvalues and lvalue references, if you have a mixture of them, into a value, which really is not something that you would really need. And you can actually, using this common reference, you can write a little macro that before applying the ternary operator, it casts the left and right hand side to their common type explicitly, which it would do implicitly, would automatically choose some common type. But by using the macro, you can specify what the common type should be. And that way, you can then get something like, if you have an rvalue reference and lvalue reference and you calculate the common type, it's a constant rvalue reference. So constant rvalue reference and constant lvalue reference would give you a constant rvalue reference, which arguably is correct. And there wouldn't be no immediate copy. You wouldn't need one, really. It's still just a reference, and it's lightweight and nice. Okay, I'm coming to the end of my talk. The const reference should never have bound to rvalues. I think that was a mistake, and probably there were factually reasons for it because of the backward compatibility you had to maintain when introducing rvalue references, and I'm sure that's where this problem comes from. Fixing C++ may be possible, but I haven't demonstrated it. I just had some funky ideas. We would need certainly a Clang implementation, and then we would need to try this on a large code base, whether that's actually feasible to do. And until then, we just have mitigations. So thank you very much.